every way we measure distances in space. Space is complicated. We make it simple. Nobody has ever stretched a physical tape measure between two stars. Every single distance in astronomy, from the moon sitting right next door to a galaxy near the edge of the observable universe, was calculated using an indirect trick, and every trick on this list only works within a specific range, handing off to the next method exactly where it starts to fail. Astronomers call this chain the cosmic distance ladder, and every rung depends on the one below it being correct. We're going in order from the nearest, most directly measurable distances to the most extreme, then we'll sort them a second way by how much this entire chain depends on trust. Because on this list, one bad measurement at the bottom could theoretically throw off everything built on top of it. Radar ranging. We begin with the only method on this list that involves physically sending something out and getting a direct, measurable response back, making it the most literal, most trustworthy rung on the entire ladder. Radar ranging works by bouncing radio waves off a nearby object, usually a planet or the moon, and precisely timing exactly how long the signal takes to travel there and back, then using the known constant speed of light to calculate the exact distance. Here's the fact that should genuinely bother you about how precise this actually is. Radar ranging to the moon, refined using laser reflectors physically left on the lunar surface by Apollo astronauts, can measure the Earth-Moon distance to a precision of just a few centimeters, out of a distance of roughly 384,000 kilometers, an accuracy comparable to measuring the distance across an entire country and being confident to within the width of a coin. Here's the part that lingers. This method is also how astronomers definitively calibrated the exact scale of the entire solar system, because once you know the precise real distance to just one planet through radar ranging, the relative proportions of every other planet's orbit, already known from centuries of careful angular observation, can be converted into real physical distances for the first time. Stellar parallax. Here's the twist. Once you leave the solar system, you can't bounce a signal off anything and wait for a reply. So astronomers switch to a trick that doesn't require sending anything out at all, just watching how a nearby star appears to shift position against a background of much more distant stars. Stellar parallax works exactly like closing one eye, then the other, and watching a nearby object seem to jump position against a distant background. Except instead of switching eyes, astronomers observe a star from opposite sides of Earth's own orbit around the Sun, 6 months apart, using the full diameter of that orbit as the measuring baseline. Here's the fact that should genuinely bother you about the scale involved. The parallax shift for even a relatively close star is so small that it was one of the last major predictions of a heliocentric solar system to be directly confirmed, not achieved until 1838, over 2 centuries after Copernicus first proposed Earth orbits the Sun, simply because no instrument before that point was precise enough to detect an angular shift that tiny. Here's the part that lingers. This method has a hard range limit built directly into its geometry. Beyond a certain distance, a star's parallax shift becomes too microscopically small to reliably measure even with modern space telescopes. Which is exactly why this rung of the ladder, however precise, can only calibrate the distances to relatively nearby stars before handing the job off to something else entirely. Spectroscopic parallax and the main sequence method. Here's the reframe. Despite the name, this method doesn't actually measure any positional shift at all. It's a completely different trick that borrows parallax's name purely because it accomplishes a similar goal. By analyzing a star's light spectrum, astronomers can determine its true type and intrinsic brightness, the amount of light it actually produces at the source, and then compare that known true brightness to how dim the star actually appears from Earth, using the difference to calculate distance, since light predictably fades with distance in a well understood, calculable way. Here's the fact that should genuinely bother you. This method depends entirely on a foundational assumption that a star's spectral type reliably predicts its true brightness, an assumption built directly on the population of nearby stars whose distances, and therefore whose true brightness, were already confirmed using direct stellar parallax in the previous rung of this ladder. Here's the part that lingers. This means spectroscopic parallax isn't actually an independent method at all. It's a direct extension of the previous rung, calibrated using it, meaning any small, undiscovered error in how nearby stellar distances were originally measured would ripple forward and quietly distort every single distance calculated using this method as well. Cepheid variable stars, the standard candles that changed everything. Here's the fact that reframes this entire category as the single most important discovery in the history of measuring cosmic distance. In 1908, astronomer Henrietta Swan Leavitt discovered that a specific type of pulsating star, called a Cepheid variable, has a direct, predictable relationship between how quickly it pulses and how intrinsically bright it actually is, meaning simply timing a Cepheid's pulse rate reveals its true brightness without needing to already know its distance at all. Here's the fact that should genuinely bother you about how far this single discovery extended the entire distance ladder. Because Cepheid variables are unusually bright, they remain visible and individually identifiable in other relatively nearby galaxies, not just within our own, meaning this single class of pulsating star became the specific tool that let astronomers, for the first time, measure the distance to entire other galaxies, definitively proving in the 1920s that some of the fuzzy spiral nebulae long observed through telescopes were actually separate, independent galaxies far beyond the edge of the Milky Way, rather than smaller structures within it. Here's the part that lingers. This single class of star is the reason astronomers use the term standard candle at all. An object whose true brightness is reliably knowable in advance, turning the simple, easily measured dimming of light over distance into a genuine cosmic ruler. Type Ia Supernovae, the standard candles that measure the edge of the universe. Here's the fact that pushes this category to its most extreme, most consequential scale. Cepheid variables, however bright, still eventually become too faint to individually pick out in the most distant galaxies. Type Ia supernovae, discussed elsewhere on this channel, solve that problem by being so extraordinarily consistently bright at their peak, always detonating at almost exactly the same white dwarf mass, that they remain individually visible and measurable across billions of light years, far beyond where any single Cepheid star could ever be distinguished. Here's the fact that should genuinely bother you. It was precisely this method, comparing the known true brightness of distant type Ia supernovae against how dim they actually appeared, that revealed in the late 1990s that the universe's expansion is accelerating rather than slowing down, a discovery that directly led to the concept of dark energy, discussed elsewhere on this channel, uncovered entirely because this specific standard candle was reliable and bright enough to measure distances at a scale nothing else on this ladder could reach. Here's the part that lingers. Like spectroscopic parallax, this method isn't fully independent either. The true brightness of type Ia supernovae had to be calibrated using galaxies whose distance was already known through Cepheid variables, meaning this rung, too, depends entirely on the accuracy of the rung directly beneath it. Redshift and Hubble's law. Here's the pivot. At the largest scales measurable, astronomers stop measuring brightness entirely and switch to measuring something else. How much a distant galaxy's light has been stretched by the universe's own expansion. Edwin Hubble discovered in 9929 that more distant galaxies show a greater redshift, their light stretched toward longer, redder wavelengths by a larger amount, in direct, roughly linear proportion to their distance. Meaning, once that relationship is properly calibrated, a single measurement of a galaxy's redshift alone can reveal its approximate distance without needing to identify any individual star inside it at all. Here's the fact that should genuinely bother you. This relationship, now called Hubble's law, had to be calibrated using the exact same standard candles described earlier in this ladder, meaning redshift distance measurements inherit every uncertainty already built into the Cepheid and supernova rungs beneath them. Here's the part that lingers. Measuring the precise expansion rate this way, called the Hubble constant, has produced two slightly different, both highly precise but stubbornly disagreeing values depending on which specific method is used to calibrate it. a genuine, unresolved discrepancy in modern cosmology called the Hubble tension, currently one of the most actively debated open problems in the entire field, hiding somewhere in the assumptions built into this exact ladder. The cosmic microwave background as a standard ruler. Here's the fact that closes this list with the most distant, and in some ways most independently confirmed, measurement of all. Rather than relying on any star's brightness at all, this method uses the cosmic microwave background, the leftover heat from the Big Bang discussed elsewhere on this channel, whose characteristic pattern of tiny temperature ripples has a known, physically predictable true size, calculated directly from the underlying physics of the early universe, rather than calibrated against any nearer object on this ladder. Here's the fact that should genuinely bother you, because that ripple pattern's true physical size is known from theory rather than borrowed from a nearer measurement. Comparing that known size to how large the pattern appears in the sky today provides a genuinely independent distance and expansion rate estimate. And it's precisely the mismatch between this independent measurement and the standard candle based measurement described in the previous rung that produces the Hubble tension mentioned above. Here's the part that lingers. This specific disagreement means one of two things must eventually give. Either there's a subtle, undiscovered error somewhere in the traditional star based distance ladder built up over the past century, or there's new physics in the early universe that the cosmic microwave background method doesn't currently account for. And right now, nobody has definitively proven which explanation is correct. Gravitational wave standard sirens. Here's the fact that closes out the individual measurement methods with the newest rung ever added to this entire ladder, confirmed for the first time only in the last decade. When two massive objects like neutron stars merge, discussed elsewhere on this channel, the gravitational waves they emit carry, encoded directly in their waveform, information about the true intrinsic strength of the event, meaning the actual distance to the merger can be calculated directly from the gravitational wave signal itself without needing to compare it against any calibrated standard candle at all. Astronomers now call this a standard siren, a direct nod to the standard candle concept, but measured through space-time ripples instead of light. Here's the fact that should genuinely bother you, because this method calculates distance from fundamental physics rather than calibration against a nearer rung. It offers a genuinely independent cross-check on the traditional distance ladder, and early standard siren measurements combined with a directly observed corresponding flash of light from the same event have already provided one of the first fully independent attempts to help resolve the Hubble tension mentioned elsewhere in this list. Here's the part that lingers. This method currently only works for events close enough and bright enough to also confirm a visible counterpart, meaning it remains rare and difficult to use broadly for now, even though it holds the distinction of being the only rung on this entire ladder that doesn't ultimately trace its calibration back to light at all. Let's sort these 8 again a different way, not by distance, but by how much each one depends on trusting the rung beneath it. On the fully independent end, radar ranging, the cosmic microwave background method, and gravitational wave standard sirens, each calculated from direct physical measurement or theoretical prediction without leaning on any other rung of the ladder at all. On the geometrically independent end, stellar parallax, calculated purely from angles and Earth's own known orbital diameter, with no dependence on any assumption about stellar brightness whatsoever. On the fully dependent end, spectroscopic parallax, Cepheid variables, type Ia Supernovae, and standard redshift measurements, each one calibrated directly using the rung immediately beneath it, meaning an error introduced at the parallax level would ripple upward through every single one of these methods in sequence. It's worth sitting with before we close exactly how young this entire scientific effort actually is. Reliable stellar parallax measurements are less than 2 centuries old. Cepheid variables were only discovered as standard candles just over a century ago. And gravitational wave standard sirens have existed as a measurement technique for less than a decade. Here's the fact that should genuinely bother you. Essentially, the entire modern scale of the universe, from the distance to the nearest star to the size of the observable universe itself, has been established within a time frame shorter than a single long human lifetime, layered on top of centuries of much older, purely geometric measurements within our own solar system. Here's the last thing worth sitting with. Every distance you've ever heard quoted for a star, a galaxy, or the edge of the observable universe traces back through an unbroken chain of calibration to the width of Earth's own orbit around the sun, measured using nothing more exotic than careful angles and patient observation. The entire scale of the observable universe, every single figure of it, was built rung by rung on top of one single geometric fact about our own small solar system. Not bad for stick figures on a rock,